Let's try a couple more quick problems here. So I want to determine the pH at the equivalence point when 100 mils of 0.25 molar NaOH is added to 10th molar acetic acid. So I have my flask, I have some acetic acid and NaOH. Now they don't tell me how much acetic acid I've added, but they do tell me it's at the equivalence point, which tells me my moles of acid and my moles of base are equal to each other. So what I could do is I could figure out how many moles of base I have. I have 100 mils of 0.25 molar, so that's 0.1 times 0.25, so 0.025 moles of my NaOH and 0.025 moles of my acetic acid as well. Since I know that my acetic acid is 10th molar, I can figure out that I have 100 milliliters of, 250 milliliters of my acetic acid. Here's my calculation to figure that out. I have 10th molar. I know I need 0.025 moles over X liters, so it ends up being 0.25 liters. So let's write out our reaction between my acetic acid and my NaOH. So my NaOH is a strong base, so I'm going to use OH minus plus my acetic acid. I form water and acetate. So 0.025 moles, 0.025 moles, and 0. Don't care about the water. Minus 0.025 moles, minus 0.025 moles, plus 0.025 moles. So at the equivalence point, I don't have any of those, and I have 0.025 moles of my acetate. If you want to do part of this in your head, that's fine. It's kind of obvious that I would end up with the same amount of moles of the acetate. But anyway, at the equivalence point, I don't have any of these. I only have acetate ion, which can undergo hydrolysis, and that's how I find its pH. So I'll write the hydrolysis equation now. So that with water, it will grab NH plus from the water to form acetic acid, and it will form some hydroxide ion. I would need to divide by my total volume here to find my concentration. So 0.025 moles divided by, I have 100 milliliters of NaOH, and I have, we figured out 250 milliliters of acetic acid, so 0.35 liters is my total. That gives me 0.0714 molar. So this is 0.0714 molar. Don't care about the water. 0 and 0 minus X plus X plus X. 0.0714 minus X, X and X. My KB expression, 5.6 times 10 to the negative 10th is equal to X times X over 0.0714 minus X. I'm going to calculate X, which is my hydroxide ion concentration. And I apologize, I just added this problem to your notes, and I don't have it in mine. And I don't have a calculator at home right now with me, so I don't know what the X will be. So you guys figure it out. Figure out what the concentration of the OH minus is, and the POH and the pH eventually. But definitely my pH at the equivalence point will be basic. It should be higher than 7. So I'm going to let you guys finish this off. Let's look at the next problem here. This one says a weak diprotic acid was titrated with a base. Now, even if it doesn't tell me that this is diprotic, I should be able to look at my titration curve and figure out that it is. How do I know that? Because there are 2 equivalence points. And I know that because there are 2 like inflections with a part that's almost vertical. So there is my first equivalence point, and here's my second equivalence point. If it was triprotic, guess what it would look like? It would, look like this, where there would be a third equivalence point right there. So I'm going to go ahead and erase that. Now, what it's asking for is, it says from the titration curve, we want to calculate pKa1 and pKa2. What is that? That's negative log of the Ka for the first H plus of that acid and for the second H plus of that acid. Well, how do you know that? Well, the pKa is equal to the pH when it's half neutralized. So let's look at the first one. Here is my equivalence point. It looks like it's at 8 milliliters of base. So what I do is I go to halfway to that. So instead of 8 milliliters, I go to 4 milliliters. Let's see if I can try to get to about 4 is right there. And so I go up to here, and then I read what my pH is. And so I am kind of estimating here, maybe it's a pH of about 3 or something like that. Now, if you were doing this on the test, the numbers would be a little bit clearer or easier to read, and also they'd give you more leeway. So I'm going to say that my pKa1 is going to be equal to about 3 or so. Okay, now let's look at pKa2. So what you do is you go to half the second equivalence point. So right here is my second equivalence point. It's at 16 milliliters. This was 4 milliliters down here. So what you do is you look at halfway between those. So 16 and 4, halfway to that. I'm sorry, 16 and 8, halfway to that would be 12. Because this is where my first equivalence point is. This is my second equivalence point. So you look at halfway between those 2 points. And so that would be about 12 or so. Let me mark that. So right here at 12 milliliters. So you go to 12 milliliters and you read what the pH is right here. And so, I don't know, that looks maybe like maybe a 9-ish or so. It's kind of really hard to read on this, but it should be close to about 9. It's definitely above 7 there, but, I'd accept 8, 9, maybe even 10. Any of those would be acceptable. All right, next is a chart that I just added to the notes this year because I felt like, titrations are really confusing. There's so many different calculations and so many ways that you would find the pH, and it just depends on if you have a strong or weak or, at the end, is it the equivalence point? Is it halfway? Is it after? What's going on? So here are the steps to find the pH whenever you're doing any titration calculation. So what you do is, first of all, you look at your acid and your base that are reacting together. You write the reaction between the acid and base. And it's always one arrow because acid-base reactions have very high Kas. They go to completion. Next, you determine the moles of the acid and the base that you're given initially. You determine which one's the limiting reactant, subtract that from everything, add it to the products, figure out how much is used up, what's left over. And then at the end, look at the substances that are left over. Some of them would be used up. You don't look at those. Look at the ones that you actually have remaining. And depending on what kind of substances are left over, you determine how to find the pH. So let's go through a list. Let's say you've used up everything and all you have left is some strong acid, like HCl, for example. That's all you have left. Well, in that case, you just use the molar concentration of the HCl. You say that's the concentration of the H+. You do pH is equal to negative log of that H+. Okay, what if what you're left over with was a strong base, like NaOH, for example, or, OH minus? Well, again, use the molar concentration for the NaOH. That would be the concentration of the OH minus. So you find the POH from this, and then pH would be 14 minus the POH. That's pretty straightforward. What if you're left with something like HF? That's a weak acid. Well, how do you find the pH of a weak acid? You got to do the dissociation of the acid. So HF yield double arrow because it's equilibrium, H+ and F-. Do an ice chart for your acid dissociation. What if you're left with something like NH3? That's a weak base. Well, how do you find the pH of a weak base? Same thing, ice chart for the base dissociation. What if you're left with something like HF and F-, or like acetic acid and acetate, or something like that, where you have a weak acid and its conjugate? Well, you could either do an ice chart, or easier, you could just do a Henderson-Hasselbalch. What if you're left with like ammonia and ammonium, a weak base and its conjugate? What do? Again, you could do an ice chart, or you could do a Henderson-Hasselbalch. What if you're left with something like a neutral salt, like NaCl? No need for any calculation. That's a pH of 7. That's pretty easy. That would be a strong titration at the equivalence point. What if you're left with an acidic salt, like NH4Cl, or just NH4+? Well, that undergoes hydrolysis. And so you write the hydrolysis of that cation and you do an ice chart. What if you're left with a basic salt, like KF or F- by itself? Again, hydrolysis of the anion and then an ice chart. So hopefully this kind of helps. Always write out your reaction, figure out how many moles, what's your limiting reactant, what's used up, what's left over. Look at what's left over, and depending on what substance is left over, this is how you determine the pH. So hopefully that kind of helps.